Using HSRP for high availability. Imagine having a car that always worked. For example, you went out to the garage, you turned it on, the car always works. And imagine further that if it didn't work, that some magical elf behind the scenes would have verified that it didn't work and swapped it out with a different car so that when you did go out to the garage, the car worked no matter what. As an end user on a customer network, we need default gateways to get off of the local area networks, and HSRP is one of several mechanisms that we can use to do exactly that in a fault-tolerant manner. How important is a default gateway for a customer? Let's start there before we talk about fault tolerance. A customer is a happy customer if that PC can get off of the local area network. And normally here's how it goes. From the PC or the Mac or the Linux or what have you, we have a patch cable that goes to a switch. And from the switch, it goes to a router that looks like one of those with the arrows going in 4 directions that has connections to additional networks. So if the PC ever wants to get out to a remote network, something that's not local, different subnets, it needs to use its default gateway. For that reason, a default gateway is a critical resource for every device on the network. So what happens if this default gateway fails? The customer's out of luck, unless you and I deploy some fault tolerance for this layer 3 default gateway functionality. There are several options we can use for fault tolerance for this customer as far as this default gateway is concerned. One option is HSRP, which I'll be demoing today. Another option would be the Gateway Load Balancing Protocol, and another one that's an open standard is the Common Address Resolution Protocol. All 3 of these options provide layer 3 fault tolerance for our customers, and here's how we can pull it off. First of all, we start off with 2 routers. That's the key. So we start off with 2 routers, and I put all of these interfaces here into a common VLAN, a common broadcast domain. And that subnet is the 10.12.0.0/24 network. And I've also put other interfaces of those same routers and a connection out to a server in this VLAN over here. And that network is, for example, the 172.16.123.0/24. And so our routers have connections to both sides, and we have 2 routers. And what we're going to do is this. The client's going to get an IP address. Now, how does a client normally get an IP address? If we had 200 clients that all needed IP addresses, probably the way we would do it is use DHCP to dynamically assign an IP address to this guy. Additionally, besides an IP address, we'd also assign a default gateway. So let's say that the router's interfaces are .1 and .2 on the 10.12.0.0 network. The default gateway that we hand out to customers, however, is going to be a virtual address. Let's say 10.12. Let's use 0.100. So the client believes that maybe it got the address of 10.12.0.50 for its own IP, and the default gateway is 10.12.0.100. Now the game we're going to play on these 2 routers, router 1 and router 2, is that they both are going to provide services for this default gateway address. Meaning, if the client ever does an ARP request or sends packets destined to that address and the corresponding layer 2 address below it at layer 2, one of these routers is going to respond and take care of the customer. So to sort it out with HSRP, they use an active and a standby router. The active router actively supports this virtual address that was handed out as a default gateway to the clients. The standby, oh my goodness, the standby just sits there all day and says, yep, active's good, he's going, he's happy, I don't have to do anything. The standby only has to kick into gear if he stops hearing the active router and he says, oh my goodness, it's been 3 seconds, it's been 9 seconds, the active router must be dead, and then he can convert his role over to active, and then hopefully the other guy will come back later. So Hot Standby Routing Protocol provides a virtual default gateway address for our customers to use. It looks and feels absolutely real to our customers. So let's put this in motion. Let me bring in a client, and he's a happy client because he can get out to the network. So if we want to take a look at the details of this client, and by the way, this is a client on this network segment. He's wired, but he's on the 10.12 subnet. And if we take a look at his information, we can use some common tools that we're probably familiar with, such as ipconfig. And ipconfig says my IP address is 10.12.0.51. My default gateway is 10.12.0.100. If we do a show ARP, that's too much iOS on the brain. A show ARP would be a great command at the CLI of an iOS router. We want to do ARP-A on this Windows box. There's no ARP entries found. It has no layer 2 mappings, or if it had them, they timed out, which is perfectly fine. Let's bring in the routers. Here's router 1 and router 2. We'll bring them in. And if we do a show interface FA 1/0 on this guy, here's the actual address that I have configured, the layer 2 address. So that's the layer 2 address for router 1, and the layer 2 address for router 2 is this. So you just have to focus on the first 4 digits. 0022 is the layer 2 address for R2, and 0011 is the address for the layer 2 address for router 1. And check this out. We do a show standby. It says, hey, check this out. The active address is this one right here, which is 10.12.0.100. That's the address that they're supporting. And look at this layer 2 address, this fake MAC address for hot standby routing protocol. Whichever router is acting as the active router is going to respond to requests for the global address, the default gateway, and this is the MAC address they're going to use. So whoever's active, which happens to be this guy, is going to be doing 2 MAC addresses. One MAC address for his IP address on his interface, and another MAC address he'll be playing with on behalf of the hot standby routing group that he's active for. And this just shows us who's active at the moment. So the active router is local, and the standby router is my good friend R2 at 10.12.0.2. So let's go ahead and test this out real quick. In fact, let's capture the traffic. So I'm going to go over here to my link. I'm going to do a capture, starting capture as we speak right now. It's capturing. And now let's go do a ping of 3.3.3.3. That's a remote resource. That should cause an ARP request for the default gateway, and then we're going to forward some ping packets. So there it goes. So I'm going to stop the capture, and let's take a look at it. And I'm doing this in real time so you can get a sense for what's really happening. So let me bring up the capture, and here it is. This is the capture I just created. Hopefully it's going to work out. And okay, there's HSRP messages going back and forth. So router 1, let me move this out of the way. Router 1 and router 2 are talking to each other. Are you okay? Yeah, I'm good. I'm there. And that's going on frequently here. And what we're looking for is our ARP request. There it is right there. So here's our ARP request. It's coming from the Intel interface on my PC, and it's being sent out as a broadcast. And if we take a look at the contents of this, it's saying, I'm looking for the IP address of 10.12.0.100. Whoever has that, please respond with the layer 2 address for that. And here's the response. And check this out. The reply is coming back from 00000C07AC00, and that's that special HSRP address. In fact, we can see it right here. That's being managed by the active router. So if we look at the ARP cache, now that we got the results back, if we look at the ARP cache on the PC, bring them back in. Now we have this MAC address 10.12.0.100, and we believe that the layer 2 address is this, and the person who's going to respond to that is the active router. So now we can do some pings to 3333, and it works. No problem. Now, case in point, what happens if one of the routers fails? So instead of just shutting down the router, let me go ahead and actually turn off the interfaces, both of them, on our router. And that way he'll be guaranteed not to be able to do any support for anyone. We'll do a show IP interface brief, and let's go ahead and do a interface FA 1/0. We'll shut it down. Interface FA 1/1. We'll shut it down. And so basically I've got a virtual interface open, but the 2 physical interfaces are shut down. So this router is no longer able to help or support anyone else. Now in the background what's happening is R2 is losing some EIGRP routing neighborships. It's also gone active for HSRP because it's not seeing those hellos anymore from the primary router. So from the PC's perspective, if we do a ARP-A, it still has that information cached, and if we do a ping, it still works. Now R2 is doing the work. If R1 comes back into play, and if we have preemption set up, R1 will take back over. So the takeaway from this is that hot standby router protocol sets up a virtual IP address supported by at least 2 routers, it could be more, to provide layer 3 fault tolerance for customers using a default gateway. I hope this has been informative for you, and I'd like to thank you for viewing.